We always talk about how much we love to dive deep into the latest research. And, well, this one is, it's really fascinating.
Yeah, this is a real head scratcher.
It kind of makes you rethink some assumptions, about how we think about security and communication and, just those fundamental things.
Absolutely.
So today we're looking at some brand new research out of Princeton in collaboration with a team from MIT. And it's all about underwater communication, but with a twist. A very unexpected twist.
Yeah, a twist that, well, let's just say it throws a wrench into what we thought we knew about keeping underwater communications private.
So let's set the stage here for our listeners. We tend to think of the underwater world as, well, a world of its own.
Right.
Especially when it comes to how things communicate down there. The physics of sound traveling in water is so different than in air, and for a long time that suggested a kind of natural privacy, hasn't it?
It has. I mean, think about it. Sound waves in water, when they hit that boundary between water and air, well, most of their energy just bounces right back down. It's like hitting a wall, acoustically speaking. Very little actually makes it through.
Right, like shouting at someone across a canyon. You might hear a faint echo, but the sound is mostly trapped within that space.
Exactly. And this basic physical principle has really underpinned our assumptions about the security of anything happening underwater. That density difference, the way sound behaves, it's all been seen as a primary layer of protection for underwater transmissions.
So whether we're talking about scientific instruments collecting data in the ocean depths or naval communications or even, just marine life going about their business, the water itself has been this sort of shield keeping those sounds contained.
Precisely. It was kind of given, that what happens underwater stays underwater, at least from a sound perspective.
Now, we should mention that there was some research back in 2018, also from MIT, that first hinted at the possibility of, let's call it, bridging this water-air communication gap.
Right. That was groundbreaking work, no doubt. They actually managed to show that you could transmit information using sound from water to air, but there was a key limitation.
Yeah, if I recall correctly, that system was more about establishing a sort of controlled communication channel.
Exactly. The sender and the receiver had to be on the same page, so to speak. They had to be configured with the same technical parameters, like data rates, transmission frequencies, that sort of thing.
So it was more like, okay, we've set up this special phone line. We know how to talk to each other, and we can send messages back and forth. But it wasn't about someone listening in without permission.
Right. It wasn't about eavesdropping. It was about creating a deliberate pathway for communication.
And that's where this new research from Princeton really takes a fascinating turn. Because they've essentially figured out how to listen in on these underwater conversations without needing any of that prior coordination or shared setup.
Yeah.
It's passive. It's covert.
It's pretty remarkable. What they've developed is a system that can detect and decode underwater signals that were never intended to be heard in the air. And they can do this even without knowing anything about how those signals were originally encoded. It's like figuring out a secret code without the key.
Okay, so I think we're at the point where everyone listening is probably wondering the same thing I am. How? How is this even possible? If the vast majority of the sound energy is reflected back underwater, what are they actually picking up on?
That's the ingenious part. They realized that even though most of the sound energy stays trapped underwater, a tiny, tiny fraction of it actually causes these incredibly subtle vibrations on the water's surface.
Vibrations. So it's not like the sound waves are jumping out of the water. They're creating a kind of ripple effect.
Yeah, think of it as a super subtle fingerprint. The sound waves, even though they mostly bounce back down, they still cause this almost imperceptible disturbance at the surface. And these disturbances, these tiny vibrations, they contain a pattern, a sort of coded message, if you will, of what's happening below.
A surface fingerprint of the sound? That's a cool way to visualize it. But these vibrations must be incredibly small. How do they even detect them?
That's where radar comes in. They used highly sensitive radar systems that emit signals that bounce off the water's surface. And because these radar systems are so precise, they can pick up on those incredibly minute changes in the surface shape caused by those tiny vibrations.
So the radar is like a super sensitive eye scanning the water surface and seeing these almost microscopic ripples that correspond to the underwater sounds.
That's a great way to put it. But of course, the radar data itself isn't the message, right? It's just a bunch of raw data about the shape of the water surface. So to translate that into something meaningful, they had to develop some pretty sophisticated algorithms.
Algorithms, of course. It's always algorithms. But these must be pretty advanced, right? To be able to sift through all that data, pick out the signal from the noise, and then decipher the message.
They are. Think about it. They had to basically reverse engineer the physics of how sound transmits between these two radically different mediums, water and air. And they had to do it without knowing the original code, the way the message was encoded.
So they're basically cracking the code without the key. And this wasn't just theoretical, right? They actually tested this out in real-world environments to see if it actually worked.
Oh, yeah. They went beyond the lab. They wanted to see if this would hold up in the messy, noisy real world. And one of their key demonstrations was on Lake Carnegie, right there at Princeton.
Now, Lake Carnegie is a pretty controlled environment, but it's still a lake, right? You've got wind, you've got waves, you've got boats going by. It's not a perfectly still, silent bathtub.
Exactly. And what's even more interesting is that they deliberately used readily available, off-the-shelf commercial equipment for this test. They wanted to show that this technology, at least in principle, isn't some super specialized top secret thing.
So even with relatively standard gear, they were able to pick up these underwater signals in a real outdoor setting. That's pretty impressive. But they didn't stop there, did they?
Nope. They took it a step further and did another experiment in a swimming pool. Now, this might seem counterintuitive, right? A pool. But they had a reason.
Controlled environment, I imagine. But also, a pool is full of noise, splashing, echoes.
Exactly. They wanted to test their system's ability to filter out interference, to separate the signal from the noise. So they had a speaker submerged in the pool, transmitting sounds, and they had a drone equipped with a radar system flying overhead. And get this, they even had swimmers in the pool to create even more random noise.
It's like they were trying to throw every possible curveball at their system, see if it could still pick up the signal amidst all that chaos. And did it.
It did. Even with all the splashing and moving bodies and echoes bouncing around the pool, their system could still detect and decode the original signals.
That's pretty remarkable. So they proved it works in a lake. They proved it works in a noisy pool. But they didn't stop there, right? They went back to Lake Carnegie, but this time with a different setup.
You're right. This time, they used a boom-mounted radar system, which basically means they had a long arm extending out over the water with the radar attached to it.
So a more stable platform, more precise targeting of the radar signals.
Exactly. And this allowed them to really focus on a specific area of the water's surface and gather some really detailed data. And what they found was not only could they decode the underwater messages, but they could also accurately identify the type of modulation being used in the signal.
Modulation, for those who might not be familiar, is basically the way the information is encoded onto the sound waves, like AM and FM radio, different ways of carrying the signal.
Right. And the researchers found that they could pinpoint the modulation type with an accuracy rate of almost 98%. And that's significant because it shows they're not just picking up random noise, they're understanding the underlying structure of the signal.
So even with the wind and waves on the lake, they could tell how the message was being packaged, how it was being sent. Pretty amazing stuff. But also a little unnerving when you think about the implications. I mean, we've now established that this technology is real, it works, and it can function in real-world settings. And it can do all this without needing any cooperation from the underwater transmitter.
Yeah, the security implications are definitely significant because now all those underwater communication links that we thought were inherently secure, well, they might not be.
Exactly. We relied on that water-air boundary as a shield, and now we're realizing that shield might have some pretty big holes in it. And this affects a lot more than just, secret submarine messages.
Right. Think about all the scientific sensors deployed in the ocean, constantly collecting data about climate change, ocean currents, all sorts of things. That data is now potentially vulnerable.
And it's not just environmental data. Industries like oil and gas rely heavily on underwater communication for their offshore operations. Their infrastructure, their data, all potentially exposed.
And of course, there are the national security concerns. While eavesdropping on submarines in the open ocean is a lot more challenging due to wave action and distances, the researchers believe it's not impossible, especially with further development of the technology.
So this isn't just some theoretical what if. This has real-world consequences for data privacy, industrial security, potentially even military strategy. It's like we've suddenly discovered a new vulnerability in a system we thought was pretty much impenetrable.
It's a good reminder that security isn't just about digital firewalls and encryption. It's also about understanding the physical world, the way information can move through different environments.
Now, the good news is that the researchers aren't just highlighting the problem, they're also suggesting ways to address it. Their paper actually includes some potential countermeasures, strategies to defend against this type of eavesdropping.
Yeah, they're not just pointing fingers and saying, look, everything's broken. They're offering solutions. And one of the key findings is that the design of the underwater communication links themselves actually plays a big role in how vulnerable they are.
So it's not just about building better defenses against eavesdropping. It's also about building more secure systems from the ground up, so to speak.
Exactly. For example, they found that some types of modulation, remember those ways of encoding the signal, are much easier to detect and decode from those surface vibrations than others.
So if you know that certain modulation schemes are going to leave a really clear fingerprint on the water's surface, you can choose to use different schemes that are harder to pick up.
Exactly. Make the fingerprint messier, more complex, harder to read. And Yaseman Gasimpour, the lead researcher on this, she's really hoping that designers of underwater acoustic transmitters will take these findings seriously and start incorporating these countermeasures into their designs.
So a call to action, not just a warning. Build it better. Build it more secure from the start. So for our listeners out there, the takeaway here is the underwater world might not be as private as we once thought.
Yeah, that seemingly impenetrable barrier between water and air, well, it's not quite as absolute as we believed.
And the fact that you can now potentially extract those underwater signals from the air using radar and sophisticated algorithms, even with readily available equipment, that's pretty mind-blowing.
It really challenges our assumptions about what's possible, and it raises some really interesting questions about what other seemingly secure communication methods might be vulnerable in ways we haven't even considered.
Yeah, it really makes you wonder, doesn't it? What other hidden channels of information are out there just waiting to be discovered? It's a fascinating and perhaps a little unsettling thought to ponder.
Definitely something to think about.
Okay, well, we've definitely given everyone a lot to chew on today. As always, thanks for joining us for another deep dive into the cutting edge of research. Until next time, stay curious.
And stay secure.